Okay, so I'm going to recap what I just finished teaching so that we can compress it into a much shorter video. The questions we looked at were 38, 52, 64, 73, and 77, which was a mock test. It's what you would get within a typical classroom test. So if you can complete all of these exercises inside of about a 75-minute period, then you know it well enough. The first question, 38, is consider the following reaction, and it shows you methanol being turned into carbon monoxide and hydrogen gas with a delta H of plus 90.7, meaning it's an endothermic reaction. You have to put heat into it to make it happen. The reaction absorbs heat. It's endothermic, as indicated by the positive enthalpy value. Part B, it asks, calculate the amount of heat transferred when 45 grams of methanol is decomposed by this reaction at constant pressure. So I calculated 45 grams of methanol, which I forgot to put grams for. And I divided by the molar mass of methanol, which is made of carbon, that's hydrogen, that's oxygen. Molar mass of methanol is 32. 45 grams divided 32 grams gives you a little bit more than a mole, 1.4 moles of methanol. And then I multiplied that by the molar enthalpy of methanol turning into these two substances, and you get 127 joules of energy required, kilojoules of energy. And then we rounded it to 3 significant figures. For part C, it says for a given sample of methanol, the enthalpy change on the reaction is 18.5 kilojoules. So now we're finding out what fraction of a mole of methanol was present. It was 0.203 moles of methanol because it was less energy than 90.7, which is what you would need for one whole mole. And then for every mole of methanol, you're going to have 2 moles of hydrogen being produced. So that's what we got here. And then we turned it into a gram amount by multiplying by the molar mass of diatomic hydrogen. So you get 0.8 to 2 grams of hydrogen after significant figures are accounted for. In the second question, which is solved here, hopefully there's not too much glare. 52. Let's read the question. Calculate. The specific heat of ethylene glycol is 2.42 joules per gram degree Kelvin. How many joules of heat are needed to raise the temperature of 62 grams of ethylene glycol from 15.2 degrees Celsius to 40.8 degrees Celsius? Oh, we forgot to answer D of the last question. Basically on that one, they asked us to reverse the reaction, and that's why you get negative 18.5, and it was 27 grams of carbon monoxide. Gives you that many moles of CO times the molar heat for that reaction. That's how you get 87 kilojoules. For the ethylene glycol question, you have 62 grams of ethylene glycol. That's its specific heat capacity. That is in joules per gram degree Kelvin change of temperature. What this means is you got to put in 2.42 joules of energy to raise the temperature of 1 gram of ethylene glycol by 1 degree. But you have 62 grams of the stuff, and the temperature change is not 1 degree, it's many degrees. So when you multiply all that together, you get 3,841 joules. Converted to kilojoules, you get 3.84 kilojoules. It's endothermic, meaning you got to put energy into it. That's why it's got a positive sign. Question 64. Oh, did I? 74, where's 209? It's on the other side of this page. Okay, 64, it says, given the data, it gives you 3 equations, and it wants you to find the enthalpy for this equation, which it doesn't give you the enthalpy value for. So the way we solve these equations is by looking for a chemical. So you focus on one chemical at a time. So I focused on N2O for the first one. I just go left to right. N2O. Which one of these reactions has N2O in it? This one does. And it has 2 N2Os turning into N2 gas and O2. Don't even worry about the other stuff. All you care about is it's got that chemical and none of the other reactions have it. So we have to focus on the third reaction to give us the energetics for N2O. You have only one N2O in our target reaction, but there's two N2Os in this reaction. So we're going to take half of number 3 to give us the one N2O that we need. And if you take half the reaction, you also take half the enthalpy. So we're going to multiply that by 1/2, and that's what we did here. Copy the reaction. The next thing we want is NO2. The only reaction that has NO2 in it is the second one. But again, we only want one NO2, but they're giving us 2, and they're giving it us on the product side. So we've got to flip the reaction and then take half of it to get only one NO2. That's what we did. We flipped it and then multiplied by 1/2. So we get what we want. Take half the enthalpy and also reverse the sign on it. Notice that here it's negative, here it became positive. And finally, on the third one, we see that we require 3 NOs in our target reaction, and so far we've only got 1. If you look at all the other 2 reactions that we've already compiled, there's only one NO provided. We need 2 more. So that reaction, this reaction, the first one provides us the 2 NOs that we need. So we just write this one as is, and the same with the enthalpy for that reaction. When you add all 3 of these together and you cancel everything that appears on opposite sides of the arrow. So if it appears on both sides, for example, nitrogen gas appeared on the left, but it also appeared on the right, so you can cancel it. Once you cancel everything that you can, everything that's left over is your net reaction. And again, you also add up all the enthalpies, and you get the enthalpy for your target reaction, which in this case is plus 155.7. Moving on then to the other board. I need a cameraman. Somebody to move my camera around, because it's not being the cameraman and the star at the same time. Makes for bad cinematography. Okay, you guys are watching again. I'm going to put it over here. Hopefully that will give you enough. The next question is 577. Actually, no, it isn't. It is the one below it. It is 573, which hopefully is visible enough. Yeah, I'm just going to adjust the camera as we talk. 73, the question asks, we're still under 12 minutes. It's actually under 8 minutes. 73. Complete the following. Complete combustion of 1 mole of acetone liberates 1,790 kilojoules. Using this information together with the data from Appendix C, calculate the enthalpy formation of acetone. So the delta H heat of reaction is equal to the delta H naught of formation of the products minus the delta H naught F of the reactants. Here's the balanced equation. We looked up all the values in the appendix at the back of the book. We're told what the heat of the reaction is, so we can set up the equation. Heat of the reaction, products, that's the products. Here's the reactants. I like to set up a big square bracket and put in all the numbers that I've looked up. Don't forget to take into account the number of moles. So 3 times 393, 3 times the 285. This we're going to call X, although you can look it up at the back of the book. Let's pretend it's not available and call it X. 0 for the oxygen. And then you just do the algebra, adding up all numbers. Pay careful attention to your negative signs. If you drop a negative sign along the way, you'll get the wrong answer at the end. So at the end, you get 247 equals negative X, which means positive X equals negative 247. It's just the algebra of the thing. So the heat of formation for acetone is negative 248 kilojoules per mole. The next question is 77. They ask you to calculate the heat of formation for octane. It says gasoline is composed primarily of hydrocarbons, including many with 8 carbon atoms called octanes. One of the cleanest burning octane is a compound called 2,3,4-trimethylpentane, which has the following structural formula. And they show it to you, might as well show it to you on the screen. There's octane. The complete combustion of 1 mole of this compound to CO2 in water leads to a delta H naught of negative 5,069 kilojoules, up here. We looked up all the values at the back of the book. What are they asking now? A,